Hello, everyone. My name is Bikash Joshi, and I'm a PhD student in University of Grenoble. This is a joint work with my supervisors, Franck and Massih. And today I'm going to present two ideas. So first of all, I'll talk about asynchronous way of doing matrix factorization. And then I'll talk about an extra regularization, which incorporates user and item similarity in matrix factorization. So to begin with, and we have already seen it today, that matrix factorization is a really popular approach in recommender systems, and notably after winning the Netflix prize competition. Here the main idea is that here we want to approximate the large and sparse rating matrix as a multiplication of two low-dimensional factor matrices, usually denoted as P and Q or U and V sometimes, and those are called user and item factor matrices. And it maps the user and items to a low-dimensional feature space. And then if you want to estimate a user's rating for an item, it can be done by just taking the dot product between the corresponding factors. And the objective function that we want to minimize is the squared error, and also we take a regularization term to avoid overfitting. And the popularly used learning algorithm is stochastic gradient descent, and this is preferred mainly because of its better accuracy and simplicity. Even though the SCD for matrix factorization, it is simple, but there are some challenges associated with it. So the first challenge is that if you go to large-scale data, and the rating matrix can be really large, and it may not fit in the memory of a single machine. And also, even it fits in the single machine, doing SCD sequentially in just one machine may take tediously long time. So there is a need for doing this thing in a distributed way. So the main idea of distributed matrix factorization is to divide the rating matrix, maybe either row-wise or column-wise, or in some cases maybe in the form of disjoint blocks. And these small blocks are dispatched in different machines, and all the machines, they update the parameters, and they communicate the updated parameters so that they have the agreement on the updated values. So the majority of these approaches, distributed approaches, they are synchronous. So synchronous in the sense that after every iteration, or in some cases after every sub-iteration, they have to synchronize the updated values. So, but if we know that in real-time scenario that all the machines, they are running different workloads. So some of the machines, they are really fast, and some of the machines are really slow. So the faster machines, they finish their iteration really quick. But in this kind of algorithms, the faster machine has to wait for the slower machines in order to synchronize. So as we can see in the figure that there is a lot of time wasted during this waiting. So what we propose is an asynchronous way of doing that, and here we propose to do the row-wise splitting, and we dispatch the data or dispatch the rating data in different machines. And whenever one machine finishes its iteration, it broadcasts its updated parameters to other machines, and it begins its another iteration immediately. And another machine, whenever it starts a new iteration, before doing that, it checks for the received updates. And if it has received some updates, it will average those updates with its local update. And then it will start its another iteration. So all these iterations, they run asynchronously, and there is no waiting time for slower machines. So even though some of the machines are running really slow, they will have a global view over all the data, and they will have all the updates from the faster machines. And there can be a clever way of doing this splitting. So rather than just splitting the data row-wise, what we propose is maybe we can split the rating matrix in such a way that similar users, they reside in the same machine. And for such scenario, we propose a new regularization, which tries to keep these user and item factors close to the average of similar user and items factors, so that we take a regularization term in their difference. So here so we'll see in the result that this helps to improve the test RMSE. And if we see in the result here, this is the first result for the first idea, that the asynchronous distributed framework. Here we can see that the dotted bold is the result for the asynchronous method, and the asynchronous method, it converges really fast as compared to the synchronous approaches, because there is no waste of time in waiting for the slower machines. And similarly, this is the result for the new regularization term that we introduced for user and item regularization. And here, actually, we consider two scenarios. First, we considered a general scenario where we present the result for both user and item similarity, regularization for user and item similarity. And secondly, we present a result for only user regularization for based on user similarity, which is more favorable in our kind of splitting of data. So we try to find the similar users in one single machine and try to regularize the updates in that machine based on that similarity. So to conclude, here I talked about like two ideas. The first one is to speed up the convergence rate of convergence rate of distributed matrix factorization using and doing it in an asynchronous way. And secondly, I talked about extra regularization term, which incorporates the idea of user and item similarity in matrix factorization. Thank you for your attention.
Any questions? It should be on.
Okay. Correct me if I if I missed something, but it looks like you first split the data and then you learn asynchronously and distributed in a distributed manner, and so if a machine is really more efficient, it will update much more than your machines, and so that means a few data, a few samples will have more effect on the model you build, and if you want to protect against that effect by blocking all the machine to do the same number of iterations. In the end, you have a machine which updates very quickly, based only on its own data and on the own database. And the other machine updates more slowly, and so the first machine cannot benefit from the information which is on the other machines. So I don't know exactly how you manage that effect. The fact that your data is split is never shared after.
So what was your question? Sorry, I missed your...
Just it's a remark. If you have a comment, is it a problem or not? If the fact that you split the data and then some machine will quickly learn on this data and the other don't care about this data, and do you get the problem or not?
Actually, the problem arises because the machines are working. They are running in different workloads. So even if you split the data in equal data in all the machines, so some of the machines will finish their iteration really quick. But the slower machines, they will, for the same amount of data, for the same amount of operating, they will take a much longer time. So in synchronous methods, the faster machines, they have to wait. Once they finish, they have to wait for the slower machines to synchronize. Yeah.
Okay, we can take the follow-up offline. Any more questions? I have a quick question. We can put the slide back on the screen, but I was looking at the convergence speed that you were comparing the synchronous and the synchronous way, and I wasn't really seeing that the asynchronous was faster. How did you determine convergence in that case?
Yeah, actually, we use the stopping criteria based on the validation set. We separated a validation set, and then we are checking like if the error in the validation set increases within the small threshold, then we stop the machine. Yeah.
But both curves seem to converge early on your plot, so that's the confusing thing.
Yeah, because even if you take the small threshold, then the synchronous machines, they converge faster in the beginning, but after some time they converge really slow at the end. But for asynchronous approach, it converges in the same flow, and even till the end, it is converging a bit faster. Yeah.
I see. Any other question? No? So let's thank our speaker again. Thank you.
Thank you.